So I just want to look back at the previous example we did with the Atwood's pulley, and I want to show you a more simplified method on how to approach it. Just because this doesn't worry so much about that direction of the force of tension, I realize that that will cause a hell of a lot of confusion for people. So what I want to do is I want to show you how you could solve for the acceleration without looking at the nitty-gritty details. So what we're going to do for this is we're going to look at the entire system. But I'm going to straighten this out. So we're going to straighten this whole thing out. What that means is I'm still going to kind of have my pulley in the center here. And then, I'm still going to have my 4 kilogram mass to the left here. And I'm going to have my 2 kilogram mass on the right. Now, if we want to look at the whole system, we have to look at what's going on. Now, in this system, you have to remember that there's going to be a force of gravity on this second mass, and this is what's going to be driving the system. Now, on this mass here, we had some forces. So we're going to replicate our free body diagrams. So I had that force of gravity acting this way. We had our force of tension acting this way. So keep in mind, I've just unraveled the problem. And then on this first mass, we had that normal force acting up. We had that force of gravity acting down. And then again, we had that force of tension acting on this mass. So this is me looking at the complete system. Now, we said that this mass is going to move down, or in this case, we're going to say it's going to move to the right. So I want to call the right direction positive. What we want to look at is, once again, if we want to find the acceleration, we want to use the net force divided by the total mass of the system. Well, the net force that we want is just in the direction of motion. And this is good. What that means is we can essentially ignore these vertical forces on the first block here, because they're not contributing to the motion at all. They're not in the direction of motion. They're just there to make sure that the block doesn't collapse through the table. So for us, the net force acting on this thing, we have that force of gravity 2. But once again, I have these two forces of tension. They're equal in magnitude, but notice they're pointing in opposite directions, and this is what I was trying to get at in the last example. So because they're pointing in opposite directions and they're the same magnitude, they're going to cancel each other out. So we don't actually have to consider tension again. So these will cancel. So what that's telling me is that the net force, or what's actually driving this system, is strictly the force of gravity acting on the second mass, and that's it. The mass of this system is going to be the total mass. So we have this m1 plus m2. So my acceleration is just going to be this force of gravity 2, this m2g, divided by m1 plus m2. So this is the same expression that we had. It will give you 3.3 meters per second squared. So that's another way of doing this problem. It cuts down a lot of the work. It cuts down a lot of the algebra. So I think there is an advantage to looking at the system as a whole. Because the main thing is, with that system as a whole, we can pretty much ignore the whole contribution to tension. But if you are asked to find the force of tension, you still have to pick one of the blocks individually, look at it, draw the free body diagram, and go from there. So hopefully this helps. The next example, I will do it with this method to highlight it. Just to, again, we want to always try and cut down on that algebra.